Yeah, welcome to another edition of it's a draftphysics.com, debatephysics.com video presentation. Alright, so sorry, I'm saying okay, I'll make the physics video, but I still got a bunch of crap on my mind from just assholes I ran across today. And you're just wondering who raises these people? How, they're just such ass. I mean, you're just saying, fuck. How did I end up on a planet where you could even create assholes? But anyway, I just don't get it. I don't get why other people haven't encountered the same reality of, God, there's a huge number of assholes. I mean, the percentage of assholes in the human population is monstrous. But anyway, it's another scientific fact that's just overlooked. So anyway, this is a corrections video. Just because I made a couple of statements in the last video that were incorrect, and so I just figured I'll correct them. And these are subjects we're talking about. So one of the subjects that I think nobody talks about. I've never seen a physicist even mention anything at all, talking about the fact that when you launch things with springs, okay, that the spring won't do the same thing for both objects. Okay, so if you have a light mass and you push it with a spring, you'll get a certain amount of energy out of the spring. It could be argued that in many cases it's like the tennis ball. You're surprised, it's 75. You throw a tennis ball at a brick wall, you only get 75% back, of what you put in. So, I would have thought the efficiency would have been higher than that. But it's pretty low. And that's because the ball's still doing this when it leaves. So you throw it against the wall, it compresses the ball launches, but it's doing this. Okay. And you can see it when they use a rubber ball that's a little more visually cleaner or more flexible, and you can see all of that wobble. So obviously all the energy isn't in the transfer. You've now converted some of the energy, instead of linear motion, you've now converted into this, oscillation. And springs have the same problem. If you compress a spring, okay, the same compression, and you launch it, you'll end up with a spring that's still wobbling after the object's left. So a guy emailed me with this, and I used the argument that it's the mass of the spring is moving, and I probably shouldn't have said anything about the mass of the spring because it's probably not a hugely relevant factor. It's just a fact that the spring does have mass, and that mass has to move the mass. So it's almost like the lever has to be made out of something, and the lever is going to consume some of the energy. So obviously some of the energy is going to be consumed in moving the physical material of the spring. But I think we all know that the motion isn't about a pure MV of the spring. It's about the tension in the spring. And so if I had just a plain spring and I compressed it and then I released it, it's going to do a similar thing, in the sense it's going to oscillate. It's going to be accelerating. It's going to reach a peak velocity, okay, and then it's going to decelerate. And what's happening in that process isn't the fact that the spring weighs something, it's got a momentum forward. It's that the whole process is basically in the one phase, most of its atoms are trying to expand, but they're expanding against the rest of the atoms that don't want to, okay, be disturbed, and they're providing the counter force. So the spring is working against itself. So when it's expanding, it reaches a peak velocity, then it has to decelerate, stop, and then change the direction. And so the energy is basically just moving from one set of atoms that are saying, I'm in the wrong position, I'm too compressed, to other atoms saying, you're stretching me, I don't want to be stretched. And that's all you're really doing, is transferring the energy from one to the other, and then back again, and then back again, and you just keep oscillating back and forth. So it's really the tension in the spring, if we can call it tension, the stored momentum, and that's what it is. It's stored momentum. It's it always has to come down to some sort of motion, and now you're just basically saying, I've converted this big object into a bunch of little things, little atoms under tension, and they're springy, they're elastic. So it all comes down to understanding electrons and the fact that they have a force that's repelling each other, and obviously if you bring them into each other, they're going to want to push away. So that's the nature of the elasticity, is in the elemental bits. The protons don't like the protons, the electrons don't like the electrons, and obviously when you're configuring them and smashing them together, the surfaces are all covered with electrons, so you're obviously pushing against electrons, and that's essentially like taking two north magnets and trying to push them into each other. It's going to create a stored tension. Now, is it physical momentum? I guess I would argue that in some sense it is, because the things are probably doing this. They're probably constantly moving, okay, in some subatomic context, which, trillionth of a second kind of motions could be. So I don't think I need a correction. It's more like just, okay, I don't mean to imply this is about the momentum of the material of the spring, because that's not the source of the force. The source of the force, obviously, is the tension in the spring material itself. The material of the spring has tension in it, and that's the source of the ultimately what will become the momentum you'll see. Alright, that's probably enough of a correction for that guy. So yeah, the argument still is that, like the tennis ball, these are inefficient, and the point is that the efficiency goes down, alright, as the mass gets smaller. So the smaller the mass, the less efficient the spring. The heavier the mass, the more efficient, because the spring will be moving very slowly in the case of the heavy object when the object leaves, and therefore won't have much energy for oscillating. So that's intuition takes care of understanding that. It's just that kind of common sense that obviously you can see the spring's moving faster. That means it's going to oscillate more, and if it's moving slower, it's going to oscillate less. It's going to have, if it's in a deceleration phase, you can understand if it's in a deceleration phase and it's still going 40 miles an hour with a light object, when it starts decelerating, that is, the object has left and now the spring's going to decelerate, and this is going 40. You can understand there's quite a bit of energy in that curve still, where if it's going 2 miles an hour, you can understand it's already way down here and it's decelerated, and so it's only got a little bit of deceleration left to do. So there's going to be very little energy left in the spring. Alright, good enough. Alright, the second one where I made an error was a kind of a, small, insignificant error, in the sense I said, when you do this reducing, okay, the volume of water. So I start off with water that has, let's just say, can't see that. 2 mass, let's say, per bucketful, we could just say. And then per bucketful, it's only 1 mass going through here, and it's going to have 2 velocity. This will have 1 velocity. Now, obviously, I didn't point out that this drawing isn't the same as some drawing where you go, well, here's a volume of stream water, and I'll just, use this portion of the water. Like, I'll split the water in half and it goes this way and it still goes this way. So if the water can still go this way, so obviously you have to double the pressure here. That's this key to this working, is that you're doubling the pressure, which allows for the volume, the velocity increase. You won't get a velocity increase if you do this. If I just separate it into two separate streams, I'm not going to get a velocity increase. But here you get the velocity increase because you've increased the pressure here. Okay, so ergo, you end up with the half the mass of the water going twice the velocity. And obviously it doesn't do twice as much. So I said 4 times. It's only twice is what kinetic energy says. Kinetic energy says the full stream, if I was to illustrate the full stream versus the smaller stream, okay. Yeah, and let's say I was moving a water wheel or something. I'm not going to get the water wheel to move faster by using this configuration. So having water, half the amount of water going twice the velocity, is not twice the kinetic energy, whatever that is. It doesn't do any more work. So again, the key to this whole thing is they say it's supposed to do work, kinetic energy, and it doesn't do any work. Doesn't move spaceships, doesn't move ballistic pendulums, doesn't move water wheels. And it's... I just don't know how more glaring examples do you need. I mean, obviously, they're saying it takes 25 times the fuel, okay, 25x, to go 5 times the velocity. Oh, I should put the x. It's not true. I mean, I don't know why every single person watching this video can't just say, I get it. That's not true. And if their theory says that, then there's probably something really wrong with the theory, because that doesn't happen. Ever. In any circumstance ever. It just doesn't happen. And going 5 times as fast, yes, it's 5 times faster, so yes, it's going to be a significant amount more energy, but it's 5 times more energy hitting a brick wall, let's say. Not 25 times more energy hitting a brick wall. And again, this sort of goes back to the Mythbuster car crash. It goes to the Bruce Yearney videos with the wooden blocks. But I mean, obviously they crashed the same car, 50 miles an hour, 100 miles an hour, and the crushing was just twice as much. It wasn't 4 times as much as the theory says. So, I have to just say, why is there no concession that this is a subject in need of some clarification? I mean, Steve Mould, I've made maybe 50 or 60 videos with that title, the lever paradox. He made a video where he did no experiment. Nothing that could be called a clinical experiment. He didn't prove anything at all. And he just made this declaration that somehow, a 2 mass going 1v goes in this side, and a 1 mass going 1.4 pops out the other side. That you lose a big pile of the momentum because you conserve the kinetic energy. And it means the inverse has to be true, that I can put a 1 mass going 1.4 into this side, and I'll get a 2 mass going 1 out this side, and I'll get 33% free momentum. I mean, how? What exactly am I missing? All right, that your belief is so strong that in light of these facts, you will not concede, or you can't say the words, yes, you're right, there's something wrong with the kinetic energy theorem. It really doesn't prove itself in actual reality. How can you not concede? Oh, I forgot you're assholes. Oh, shit. Oh, yeah, the answer was right there in front of you the whole time. Oh, nothing mysterious. sheesh. Okay, never mind. Alright, so the other error I made was describing this drag is not really a thing argument. And this one's big. Okay, this is a really big physics concept in terms of understanding the nature of energy in the universe and the function of force. And so it'd probably be best if you did understand some of my other simple arguments regarding the nature of photons or bosons and the fact that it is particles, frankly, and then a photon is just a stream of bits at a distance, and that is the frequency. The energy is in these little components, and that, frankly, to make a simple argument, it's a tipping point argument. Okay, if I have 3 baseballs and I throw the baseballs really, with quite a bit of time in between them against something, especially something elastic, and we know atoms are elastic, the electrons are elastic. So if I hit them, then they're going to do this and find their equilibrium again, and this, and stay, and okay. But if I hit the baseballs, throw the baseballs quickly, with less time between them, and I don't allow the elastic rebound when I'm adding more energy, I can get this to move not only just faster, but I could tip it over. That is, I could eject an electron. So I can give it enough momentum to leave. So if I hit it while it's still moving, I add more energy to it. Alright. And let's understand it's a speed of light force. So if you're going 5 miles an hour each time you get hit, because it's a tiny force spread over a big object, you would understand that you're not going to gain so much velocity that the force is no longer effective. So that's not going to happen. But anyway, so it's something to understand that higher frequency light isn't higher energy. It just means that you're delivering the energy in a way that's more likely to disrupt an electron, and that's all. It's not more momentum. It's just that the momentum is delivered in such a way that it has more of an effect. So it's like putting a point on an arrow. Again, these are not really hard arguments. To get absolutely no reasonable response from people who should know better. I mean, they know enough physics to know these are reasonable arguments. Anyway, all right, so in the case where you move an object into a force, so obviously, okay, if I left things just this way, and just imagine this is happening every second, okay, there's 3 a second from this side, 3 a second from that side. You could imagine an object and it's just going to stay there, right? I mean, it gets hit with this one and it gets a tiny bias that way, but then this one hits and it gets a bias and it just does this. All right, it doesn't go anywhere because it's under an equal amount of pressure from both sides. So now I add a fourth, right? And probably should do it with a squiggly line or something. So now what's going to happen is that, and this is a force that shares its momentum. So just understand, a little arrow basically is going to stick to the object and give it momentum. So now it's part of the object, and that's the nature of its momentum is an absorption. Absorption means it's transferring its energy to the object and still there. Now the energy is in the object, and now it can leave again, or it can stay. Anyway, all right. So now I've given it a bias. Okay, so now it has a bias in this direction. It's going to go into this field, and the simple argument is yeah, but this all exists. All right, in the sense that it was inevitable that this was going to hit me. So me moving towards it doesn't change anything. And again, we're talking about a speed of light force. So we're saying this little tiny bit of motion of me moving into the force isn't going to mean anything. It's the same impact, same punch is going to happen. You're just changing where the punch happens. So instead of the punch happening here, the punch is going to happen here. That's all you're changing. It's the same amount of energy is going to hit it. You're just changing when it's going to hit it. That's just such a key thing to understand. So if you really count the little arrows hitting the object, right? Just imagine this object's big enough to get hit by all these arrows. I'm, assuming you can do a little bit of this on your own. I don't have to explain everything to you. But anyway, all right. So it hits the force earlier. It stops, but the trick is that when it did go forward into this force and hit this one sooner, it's going to hit this one's going to hit it later. So these are all lagging behind now, but they're eventually going to show up, right? So a millisecond later they show up, and frankly you added the 1 and there's still 3 more. We used this one, but we still have these other 3, and they're going to get here and they're going to push with 3, so I'm going to have a total of 4 again. So no matter what happens, I'm still going to be stuck with that 4. So this is going to travel through space. It's going to go with 1 velocity this way, then it's going to stop because it's dragged to a halt. It's not going to go the opposite way, it's just going to stop, and then it's going to go forward again because it's got this bias, and the bias is going to keep showing up. And so this is how it's going to move through space. So there's no drag per se, until I can't stop the thing until I actually add an extra bit of force here. I have to add it. I have to give that side an extra piece to compensate for this extra piece. And if I count how these things hit, like I said, I could do a simulation, I suppose. This is pretty easy to simulate. So the only way I can get it moving is to add a force. And the only way I can stop it from moving is I have to add a force. I can't stop it with drag. Drag only changes when it gets hit. It doesn't change that it will get hit. And that's hugely important. Alright, so I'll draw the part where I made the error. Alright, so I did the thought experiment, the supposing, well, what if we could do a hyper jump? That is, I could just take something that was here and I could move it without going through any force or doing anything, and just change where it was, hyperspace. I could just make something poof in another place in space. The interesting thing to understand is what have I changed? And you could understand that all of this energy, that all the energy going this way, okay, is now capable of hitting this object. So it's not only going to get hit by this, okay, which it was going to get hit by anyway, but it jumped over a whole pile that it never got hit by, that's now still in the field, and now is going to hit it. And the fact is that the stuff going this way, it evaded. So all the arrows going this way here never hit it. Right? So they never got to push it that way. So you have a huge bias, okay, and that would represent that the object now would have a huge velocity this way. I mean, a gigantic velocity this way. I supposed that it would go backwards this way, and that was just wrong and stupid. So that was my mistake. Obviously now the bias is going to be huge that way, because this whole block of energy, all the energy here going this way, is new added energy. The energy it jumped over, and then it evaded all the energy going this way. So any energy going that way, it evaded, and it can't get to it. So it's going to be less energy. This part and this part are still the same, but those bits here and here are the ones that have changed, and it's reversed. One of them now will hit it and one of them won't, and so you'll have a huge bias in the direction that you hyper jumped. Now you have a huge velocity that can only be mitigated or changed by adding a huge amount of energy to stop the damn thing. So depending how far you hyper jump, you would have a very large amount of energy to compensate for. Now, obviously, I don't believe you can ever do any of this hyper anything. This doesn't happen. So it's just a thought experiment. What if the universe allowed such things? It doesn't. Okay, it's a material universe, and nothing poofs in and out of existence. None of that crap happens. There's no antimatter. All that crap is nonsense. I don't know why people believe it. I just don't, because the evidence just isn't there. I mean, you could go back again to the positron. 4 different people did the same experiment. 3 of them said, it's just a proton going fast. And then one of them says positron. Yeah, you know, it's just what they decide to define it as. It's not a real thing. Somebody invented this idea that somehow electrons have angular momentum, that somehow they're spinning or doing something equivalent to it, that they have some kind of magnetic field. So they're negatively charged. They can't be a dipole. I mean, not even understanding that. I mean, just, I mean, not to be able to understand the huge connection, right? Everybody knows there's a huge connection between electricity and magnetism. And I really have to say, and they, you know, you have Maxwell's drawings that just show you what a charge looks like. And you're saying, I have to explain to people that electrical dipole and magnetic dipole, you're talking about the same concept of the idea of electrons and protons. You have to have an electron and a proton. There, that's a dipole. That's a what they call a neutron. Okay, but that's all it is. It's a dipole. It's not that it has no charge. It's that it has the same amount of charge, positive and negative. And that the magnetic monopoles are exactly the same. These are the magnetic monopoles, electrons and protons. And the fact is, when you arrange them, they'll produce a pattern to the world, okay, that's going to be distinct, and it's going to have an appearance to it. So when you build a whole atom and you have all these things, you know, all these electrons and protons all over the place, they're going to excrete a pattern, and the electrons and protons will be able to see that pattern if they're polarized. If they're polarized, they'll see it. If they're not polarized, they can't. I mean, it's not, you know, but it's just so, it's so obvious that the electrical dipole, if I could call this an electrical dipole, behaves, looks like, functions as exactly the same as if it was a magnet. Okay, and you had a north side and a south side. It's going to behave exactly the same way. And so, you know, them saying that this has another kind of polarity, that somehow the negative thing isn't really a negative, that somehow it's another little magnet or something, is just, that's an extraordinary claim that should come with extraordinary, or at least superordinary evidence. You know, there's just no reason to think electrons are polarized and creating a magnetic field all by themselves. Like if I had an electron right here, that electron would be excreting some sort of magnetic field. It's excreting electron field, and that's it. It's radiating. You know, I mean, obviously I've made all these arguments in other videos, but I mean, charge can be understood as the simple rules that these two objects are in a field of force that's also polarized. And the key function is if you hit the same force, if a proton force hits a proton, it sticks and pushes it if it isn't moving already. If it's already moving against that motion, then it just reflects, and the bit reflects off the proton, so it loses its momentum, and it reflects 2 bits of force. But the key one is if the electron force hits the proton, it goes straight through and just changes into an electron force. And now you can understand why protons and electrons attract each other, is because they can't push on each other. So proton force just goes straight through this electron, pops out again as electron force. So it starts as electron force. If it hits a neutron lengthwise, it comes out exactly the same as what it came in as, and nothing happens, nothing moves. And that's the key. That's the pattern creation. And with that simple rule, you end up with an electron that only reflects. So even though it gets hit by red force and blue force, the only thing it ever reflects is the blue. And the red goes straight through and comes out blue. So it ends up looking as if, so this mixed force comes in, and all that comes out is the blue. So all the red is converted. So the blue is doubled. So the amount of blue force is now twice as much in the universe. When an electron exists in space, it's creating half its energy, so to speak, half its pushing power, has now been synthesized out of the red force. And obviously the protons are doing the same thing in reverse, so obviously there's still the same amount of red and blue in the universe, because there's the same number of protons and electrons theoretically in the universe. So you don't change anything in terms of the big universe, but obviously when you're in proximity to these things, and again, this is exactly Maxwell's drawings. So Maxwell's drawings of charge are exactly this idea. Okay, that if there was another proton here, obviously it's a sticking force, so it would give them both momentum. The force would bounce back and forth. It would give them both momentum, eventually, push them away from each other. And obviously the red and blue would end up being pushed by the red force here. The red force pushing on the proton, but no red force can come from this side to push this proton, right? So if this blue's here, no red force could get through here and get to this proton. So obviously it gets pushed in. And the same is true in reverse. The blue force is pushing on the electron from space, but no blue force can go here without getting converted into red force. So obviously there'd be a big vacuum between the proton and the electron. That's why they attract. I mean, all of this is explainable. And I have explained it, not because it works perfectly. I've shown the simulation. And this creates dipoles. This creates electron, proton, electron, proton. It creates objects that become atomic nucleuses. It solves. It's a model that creates what actually exists. And it does it with very simple mechanics and rules. No wooey fields of any kind. Just a universe of force moving the speed of light, electron force, proton force, two kinds of force, two kinds of matter, electron, proton, and three interactions. Absorption, sticking, reflection, and conversion. And with those simple mechanics, you end up with Maxwell's equations. Fact. All right. I mean, all of the inverse square law, it's all in there. Yeah. Anyway, so enough said. Till the next time, and such and so forth, and whatnot. Yeah, probably enough. Well, those are the three mistakes I noticed anyway. Not really two of them are mistakes. One of them is just a semantics argument about the nature of energy storage. Okay, so till the next time and such.